The next talk is by Daniel Smith. Due to his timing mismatch, we have moved his poster session and into this session 2. His poster will be presenting on Sapphire Diffractive Axicon milled with femtosecond laser ablation for imaging application. Yes, Daniel.
Sure. Thank you very much. Just get my screen up for you. Hello, everyone. My name is Daniel Smith. I am a PhD student at Swinburne University of Technology, working in collaboration with the University of Tartu. So today I'm going to take you through the poster Imaging with Diffractive Axicons Rapidly Milled on Sapphire by Femtosecond Laser Ablation. So I only have 10 minutes or so let's get into it. Today you're going to learn how single pulse femtosecond laser fabrication can produce a flatter and smoother profile for surfaces known as binary surface axicon and binary surface photon sieves. Then you'll see some results, how these diffractive optical elements can be easily upscaled from 5 by 5 millimeters to even meter larges in easy amounts of time. And then you'll see how these diffractive optical elements can be used in imaging applications, which we will apply a nonlinear noise filter to screen the noisy images. So for now, let's target that fabrication technique. So what is femtosecond laser fabrication? Well, it's a process by a laser uses pulse duration pulses of 200 femtoseconds to rapidly bombard a surface. This causes high intensities to build up on the surface of the material and cause essentially an explosion, which ejects some material. This rather violent yet controllable method allows us to fabricate any number of 2D or 3D devices at our will. Essentially, the limit here is your imagination. Now, for us, our material of choice was sapphire. Sapphire has a spectral transmissivity from 300 nanometers all the way up to 6,000 nanometers, which means if we want to use it as a diffractive optical element, we have a plenty wavelength range to use it for. Sapphire is also strong, and it takes something on the same toughness as diamond to scratch it. It also has a crystalline structure, which adds to this toughness. This all culminates into being something that is hard to ablate with laser. In fact, we used a 5 microjoule beam to ablate the sapphire, which translates to 69 terawatts a centimeter squared. Now, you might be wondering, well, what's that in reference to other things? Well, the ablation threshold of sapphire, essentially the minimum terawatts a centimeter squared that you need in order to get ablation, is about 10 terawatts a centimeter squared. And now, for reference, in the greater scheme of things, if we compare that to other explosions on Earth, which would occur at about the 2,000 terawatts a centimeter squared, that's the sort of energies that we're dealing with. So it's quite a lot. Now you might be thinking, okay, so then the diffractive optical elements must be quite deep. Well, let's get into that. So first of all, what are binary surface axicons? What are binary surface photon sieves? Well, the binary part refers to as the 2 steps. You have a flat surface and a step down, and then continuing on with the flat surface. The surface part of it refers to that it's inbuilt into the sapphire. So if we have the optical images here from the microscope, we have A for the axicon, B for the photon sieve, and C for the sparse photon sieve, where the difference between them is the separation of the pulses. The axicon has overlapped by about 30%, and so you get this valley rather than separated points like you get for the photon sieve, which is separated by each single pulse. Then the sparse photon sieve has these little gaps in between each one that you can see. If we look at the depths of these using the optical profilometer, we see that the axicon has these valleys. We see that the photon sieve has these spots. Now, while we're at this point, we should be noted that these spots that the photon sieve has, they are actually Gaussian in shape. And that's because the Gaussian nature of the laser is imparted during the laser ablation process. So the depths of these are actually quite interesting. The axicon was 360 nanometers, the photon sieve was 412 nanometers, and the sparse photon sieve was 420 nanometers. You might be noticing something odd here. Why does the higher intensity, the Axicon with its overlapping pulses, have a shallower depth? Well, there's actually a process, a mechanism in play here. When you have these overlapping pulses, it kicks up a lot of debris, and that debris settles back on the surface, causing the interface between the laser and the sapphire to change. And hence you get a harder to ablate surface. But we can use this. This is all by design. And you can see how as you get wider pulse densities, you get deeper and deeper depths of the laser. Now, it's all by design. So why did we have these depths? Well, there's a relationship between the thickness of the device that you want, the wavelengths that you want to interact with, and the refractive index of the material. So we wanted to target 600 nanometers of light for imaging purposes. And if you put that into the calculation, you get that you want your depths to be about 300 to 400 nanometers, which is what we have done. Okay, that's good. Have a look at these Axicon's intensity profiles, A for the Axicon and B for the photon sieve. By visual inspection, you can see that the Axicon has these smooth concentric rings, while the photon sieve simply does not. This is a consequence of the overlapping pulses. Now, if we have a look at their normalized intensity profiles, the C for the Axicon and D for the photon sieve, then let's overlay them one on top of each other for direct comparison. The Axicon has this large central peak, while the photon sieve simply does not. Now, if you wish to simulate some of these results for yourself, you can do so. The intensity pattern observed at a distance v from the diffractive optical element is given at the convolution of the complex amplitude with the quadratic phase function q1/v. So if you wish to simulate that, you can. Now, we did perform imaging, so let me show you some imaging results. The imaging is shown in the bottom left here. Now, we performed real life in laboratory conditions, the imaging at 5 centimeters and 6 centimeters. Then to clean the noisy images, we used a nonlinear noise filter to get the images C and D. We then performed synthetic imaging with the letters A, P, H, and B, again at 5 centimeters and 6 centimeters. And again, applying the nonlinear noise filter. What you'll notice is, and what's really important, is that the synthetic imaging and the real-life laboratory images are almost exactly the same, which is really good. Okay, so what does this all mean? I've shown you these diffractive optical elements that can be used for imaging, that can be useful for astronomy. But what's the next step here? Well, let's take a look at that astronomy for a second here. The astronomy applications are these large telescopes that converge light to very small focal spots and end up running against diffraction. You get this airy disk where the central peak has been taken away by these other disks on the outside. Axicons can help solve to fix that. Axicons have, as we discussed before, a large central peak, which means they're keeping their light all on the optical axis, which means they're resisting that diffraction property. Okay, but however, Axicons have this low light throughput, so maybe some more work needs to be done in this area. But what about more conventional means, say photography? Axicons also have a large depth of field. They keep all their light on the axis for a large area, for a large distance. So that means something that's in focus is going to have that large depth of field. It's always going to be in focus for a while, which means if you have a light setting with lots of light to mitigate the low throughput systems, it can be used for photography applications. All right, so let's wrap this up. The fabrication time was only 10 minutes using the femtosecond laser fabrication method, and for a 5x5 millimeter area, meaning it can be easily upscaled to meters or larger in a matter of hours. The method of fabrication enhanced the imaging capabilities, and we believe this direction of research will enable the fabrication of large area structures suitable for incoherent illumination and astronomical imaging applications. All right. Thank you very much. Please, if you have any questions, don't hesitate to ask.
Yeah, thank you, Daniel, for the wonderful presentation. Let me see, is there any questions? And to the audience, this presentation and the poster will be graded for the award. So let me know if you guys have any questions. Okay, there is no raise hands, there is no comment. Yeah, I have a couple of questions. In your result, the C and D, the sectional profile.
Yes.
What
Here
is
and
the
here or
difference
up
in
above?
what is the difference in the FW HM of between those two?
Okay, that's a very good question. I'd actually have to look into that a bit more. I didn't get around to doing that analysis. However, that's a very good point, and I will make sure to follow up with you on that.
Okay, and also in the figure E, like what is the axis, like the X and Y?
Yep. So simply that it's the normalized intensity. So think about what we have in C and D here. But just overlapped on each other.
But in the C and D, the normalized intensity is up to the 1, right, in the y-axis. But
correct.
In here, why there is a huge difference?
Here, because they've been, I believe they've been, sorry, because now they're with respect to each other. So in the C and D, they are simulated where the 1 is the maximum and 0 is the minimum. So in the E where we overlap them, we have to do it with respect to each other.
Okay, so it's like with respect to each other because in the description I saw that it's like a normalized intensity profile. So I thought you just compared. That's why I was thinking like there is no point in comparing that, right? Directly.
I understand.
Yeah. Yeah. So nice presentation. And let me check again if there is any questions in the chat. And yeah, there is nothing. Yeah. Do you have any other questions, Andrew?
There is a raised hand by Igor.
Yeah, there is a raised hand by Igor. Yes, Dr. Igor, you can ask a question.
Thank you. Thank you for your talk. I'm kind of curious of your production system. So, but you kind of stuck on this B-value production. So you have one depth only production. My question here: can you make deeper, or I don't know, provide gradings for your structures? So your yeah. So can you get the question?
Yeah, I mean, he meant multiple levels. Can you achieve multiple levels in using your technique?
We are actually experimenting with that. So technically we can do one pass by over the surface to get the first depth and then do a second pass by. So like a reverse way you do it. You do the deepest parts first and then you work backwards up the levels. But yes, this is possible, yes.
So, but do you have any limit? So how many levels can you do?
That's yes. There is a limit because when your laser is focused through the objective, there is a depth of field. And if you go down too far, you start the waistband of your laser actually goes up against your surface. And so it disrupts the amount of laser light that's being focused down into the depth. So there is a limit. I'm not sure what that limit is in practice. I'd have to look that one up for you. I'm sorry.
No, it's okay. Thank you.
Yeah, it's excellent work. You got more suggestion and the questions. That shows the work is more worth, and we hope it will be like more progressive work in the multi-depth thing. You can achieve success in.